In this video, we're going to look at the definition of the derivative. The derivative is one of those things that you're going to talk about pretty much the entire rest of the time that you take calculus. So it's important that you understand what it actually means, what it describes, and that's what the definition helps with. Okay, so here we see definition of the derivative, and we can read, it says for a function f of x, we define the derivative of f at x equals c to be this limit. Limit as h approaches 0 of f of c plus h minus f of c all over h, provided this limit exists. And that limit should look familiar to you. That is the same limit that we use to define the slope of the tangent line. Okay, so that's one important idea here, is that a derivative represents the slope of a tangent line. We also know that that represents an instantaneous rate of change. All right, so that's an important idea, understanding what a derivative means. We started with these geometric and instantaneous rate of change ideas to help develop this definition, and now we're just giving it this new name called the derivative of a function. Okay, but when we did this for other functions, we did this, for example, for y equals x squared, and we looked at that at some different values of x. So one thing you might have noticed when we did that definition for slopes of tangent lines was that we were kind of doing the same algebra over and over and over again. So one thing that we maybe want to do with this definition is think about this kind of more in general, so that we're not necessarily thinking about at a specific x equals c, but in general at many values of x. Okay, so here what we see is another version of that definition. One thing that you will notice is that this is just the derivative of f, but not at a specific value of x. We've got the same definition here, except that in place of the specific c value that we were plugging in, we've got just a generic x. And so this limit, we'd be interested in all values of x for which this specific limit exists. So this would allow us to think about this for many different values of x. All right, so the other important thing about these definitions is that in math, we don't always like to write things out in words, and so we have some symbols that we use to describe the derivative of a function, either at a specific x equals c value or more in general. So we're going to talk about some symbols. I'm going to scroll up just a little bit, and we'll talk about some different symbols for the different kinds of definitions that we might be interested in. Okay, so one type of symbol that we use is what's called a prime. It looks like an accent mark, sort of, in French or Spanish or other languages too. And so we would read this f prime of x if we were interested in it for all values of x, or f prime of c if we're interested in that for c. So we call that a prime. And that just indicates the derivative of f, either at all values of x or at a specific value of x, f prime of x. That's one of the symbols we use to denote derivative. So I could go up here in these definitions and just add that in, that f prime of c is defined to be that, or f prime of x is defined to be that. We have a couple of other symbols that we use sometimes. So remembering that these are really about slope, we use something that maybe reminds us a little bit more of slope. So this is read as dy over dx, and so that really helps you remember, essentially, like we're thinking about this as a change in y over a change in x, or a slope. And so that would be a symbol that we would use for a generic derivative at any value of x, or if we're interested in that at a specific point, we might write dy dx, and then we might write evaluated at x equals c. So that notation would indicate a slope of a tangent line at x equals c, or derivative at x equals c. All right, there are a few other notations that you'll see when you look in your textbook or in some of the printed materials that we have for class, but these are the big deal common ones that you'll see most of the time, so those are the only ones I'm going to talk about in the video. You should make sure you look in the book to make sure you're familiar with those other symbols as well. Okay, we're going to look at some examples of using this definition to find derivatives of functions. All right, so here's one pretty straightforward example. The next video that we'll look at have some slightly more complicated versions, but we're going to kind of just get used to the definition and the symbols here as well. All right, so the first part of this problem says find the derivative of f of x equals x squared, and we are going to do this using the definition. If you've had some calculus before, you may know some shortcut rules. For right now, we're going to do that using the definition. On the first exam and on anything that says using the definition, you'll need to make sure you do it using the definition. Okay, so I'm going to start by just writing down the definition. F prime of x equals limit as h approaches 0 of f of, here I want to do this just in general, not at a specific value of x, just in general. So f of x plus h minus f of x all over h. Okay, so that's the definition of the derivative, and then I'm going to just apply that to this function. And so unlike the other problems we did before, I'm not plugging a specific value in for x. I'm just putting that entire x plus h into the function in place of x, and then f of x, that's just the original function, all over h. Okay, so now I have two letters here, and so the algebra is going to be pretty similar to what we did before, but just more letters. And I need to remember at the end that h is what is approaching 0. All right, so here we go. Let's go ahead and expand out the x plus h, the quantity squared. So we have to FOIL that. X plus h times itself. X squared plus 2hx plus h squared. And then I have minus the original function x squared all over h. Okay, as before, I'm writing that LIM out front of every single step. And just like when we did this with numbers, we expect a lot of cancellations to happen here. All right, so when I notice I have the x squared and minus x squared term that add up to 0, and I look at the terms that are left, I might notice that I have a common factor of h. So if I factor that out, then I can cancel that with the h that is in the denominator. So I am left with the limit as h approaches 0 of 2x plus h. Okay, so I have two letters here. It's important to pay attention to what variable is approaching 0. H is approaching 0. So I'm taking the limit as h approaches 0, and at this point I have a polynomial, so I can use a substitution shortcut theorem. I get 2x plus 0. I'm not putting in 0 for all the variables. H is what's approaching 0. X is just x. All right, so I get 2x. All right, so there's my derivative of f of x equals x squared using the definition, and that is a function of x. All right, so that's the first part of what they asked us to do. Okay, so f prime of negative 7, that means I'm going to take negative 7 and put it into the f prime function in place of x, so I'll have 2 times negative 7, and I'll get negative 14. All right, so let's talk a little bit about what that actually means. That means that on the graph of y equals x squared, f of x equals x squared, at the point where x equals negative 7, so if I think about the graph of y equals x squared, when x is negative 7, going to be way over here, and the y coordinate of that point would be negative 7 squared, negative 7 comma 49. This negative 14 that I just got here represents the slope of the tangent line to that function graph at that particular point. So that's what that negative 14 represents. That's a slope of a tangent line at x equals 7 on the graph of the original function. Okay, so then we could use that to write the equation of the tangent line or whatever else we might be interested in. Okay, so let's go ahead and do these others. F prime of 0 equals, we're putting 0 into the f prime function in place of x, so I get 2 times 0, which is 0. All right, so again, what that means, that's a slope. That means on the graph of y equals x squared at x equals 0, would be at the origin, the slope of the tangent line is 0. So I have a horizontal tangent line at that point. And then the last one it asked me to find here was f prime of 4. So I'm putting 4 into my derivative function in place of x. I get 8. What that means is that on the graph of y equals x squared at x equals 4, that would be the point 4, 16 on the graph of y equals x squared, the slope of the tangent line over there is positive 8. So I have a positive, fairly steep line with a positive slope. All right, so that's what those mean. All right, so we're going to look at one more function here, which has a little bit of an interesting detail that we want to kind of go back to the definitions and add one little detail to those definitions from before. But let me show you the example first. So this problem asks us to find the derivative of this particular function at a specific point. So we really know how to do that already, except if I think about what this function actually means, that is a square root function, square root of x cubed. And it has a restricted domain. It has a domain that is only x greater than or equal to 0. Or I'll write that in interval notation, 0 to infinity. And so when I try to use this definition for finding the slope of the tangent line or the derivative at x equals 0, which is an endpoint of the domain, I technically have a little trouble with the definition as it's written, because I can't really do a limit on both sides of 0. So when you look at the definition of derivative, what we had on the very beginning of this video, you'll usually see what we had typed there. But sometimes if you read the fine print, there's a little bit of fine print that indicates that at endpoints of the domain, so for either of these definitions, if we're at the endpoints of the domain, we're going to use appropriate one-sided limits. Okay, so we have to think about what is the appropriate one-sided limit to use. Okay, so when I think about this definition of this derivative, f prime of x, I could do it in general, or it's usually easier if you're only interested in that at a specific point to go ahead and plug in the point at the beginning. So the last problem actually specified that we wanted the derivative as a function and then evaluate for many values of x. But here we're just doing it for a specific value of x. All right, so I'm writing down the definition as it is in those boxes here at x equals 0. But when I think about doing this limit, we know that when I see a limit as h approaches 0, that really means that h technically should approach 0 from the right, and we also need to consider what happens when h approaches 0 from the left. But if I think about the domain of this function, when we're talking about h approaching 0 from the left and the right, when h is less than 0, this 0 plus h would be less than 0 and not in the domain of that function. So this is what it's talking about when it's talking about using appropriate one-sided limits. That really for this function, if I'm going to define the derivative and be really correct about that, technically what I have written here needs a little bit of a modification. I'm going to cross it out and write the better version right below. Okay, so because that point is an endpoint of the domain, we need to use the appropriate one-sided limit here. And for this one, we really can only be on the right side of x equals 0 because that's the only place we have actual domain points of the function. So this is the appropriate one-sided limit for this function because of the domain. All right, so when I plug in 0 plus h into the function in place of x, I will have 0 plus h to the 3/2, or that's just h to the 3/2. And then when I plug in 0, I will have 0 to the 3/2 all over h. 0 to the 3/2 is just 0. So this limit becomes the limit as h approaches 0 of h to the 3/2 over h to the first power. If I then use some properties of exponents to simplify that, I can subtract exponents. And I end up with h to the 1/2 power, which means square root of h. And so I have a power rule for substitution shortcut that I can use for something like this. So I get really just 0 to the 1/2, which is 0. Okay, so again, what does that mean? That means that on the graph of the original function, whatever that graph might look like, it's got 0 as an endpoint. And it passes through the point 0, 0. When I plug in 0 to the original function, I get 0. And whatever the graph of that might look like, that's maybe one you don't necessarily know what it looks like. But at x equals 0, the slope of that tangent line to that curve at x equals 0 has slope 0, flat tangent line. Okay, so we're going to look at some more examples with more complicated functions in the next couple videos.